Good morning, ladies and gentlemen. Uh, Welcome to the first talk of the day. Our speaker is Kelin from the School of Physical and Mathematical Sciences of the Nanyang Technological University, and he will talk about mathematical AI for molecular sciences. Please welcome.
Thank you for the introduction. So today I'm going to mention a little bit about how to combine with math with AI for science and then use it in the molecular science. So AI for science is an area that gets more and more attention recently. And one of the milestone works in this area is AlphaFold. So recently we have AlphaFold 3 just come out. So in fact, what really attract attention is in the AlphaFold 2 when they have a performance around 90, which is comparable with the highly accurate experimental data. So what this AlphaFold did is just translate the gene sequencing information. This ATGC is kind of nucleic acid into the structure information. So here, the detailed structure information means that you know each atom, what are the atom types, and then the atom coordinate for these protein structures or molecular structures. And whenever you have these structures, you will be able to say much more about the function. You will be able to design certain drug, design certain antibody. You can do protein engineering so that you can play all kinds of these important games. So that's why these things, AlphaFold is regarded as a big breakthrough for the structural biology. Some people even believe it has solved this kind of holy grail problem in structural biology and make a lot of structural biologists out of a job. But and then actually, this whole AI for sciences really blow up in 2014 when the 2 Nobel Prize, all goes into AI-related, science works. So this is about AI for science, but one area that actually not really, get enough attention is about AI for math. So Terence Tao is one of the big guys that really, trying to driven this area. So there are 2 major progress in this area. One is this Lean or Lean Dojo type of software. So essentially, what it does is to translate the mathematical theorem or mathematical subjects into the machine language. In this case, in this particular Lean language. So in this way, it can automatically help you to track if your improvement is correct. Some people even believe that with the progress, later they may help you to automatically prove something, right? Prove certain conjecture. Another very important progress is in this Olympic Games of IMO. So 2014, this Alpha Geometry team, they have designed their software's Alpha Geometry, and they have a performance just slightly inferior to the gold medalist. Just a few days ago, so you see that this posted July 2022, so I think it's a Monday or Tuesday, and then this DeepMind team, they have already got performance that is equal to the gold medal. So IMO has officially admitted, and actually OpenAI also have a similar performance, but somehow they believe that they didn't follow the strict rule of IMO. But anyway, this shows you the huge progress in these kind of areas. Okay, and I think most of you can already feel that this AI things is just like a tsunami coming towards us, right? You have all these kind of interesting AI models. I don't even want to go to details. And then the soaring AI power to solve almost like, all kinds of tricky questions. So then, as a mathematician, when we see all this progress in AI areas, I think most of you are wondering, somehow, can mathematics play a role, or can mathematics contribute to some intrinsic problems in the AI models? In fact, actually, in this AI business, there are 2 very fundamental challenges that are directly related to mathematics. So first one is called data representation. So essentially, all these things goes into the AI models is a certain type of data. And this data has to be translated into a mathematical model first. So for instance, I want to study the facial expression of these people. Usually is that I take a picture, right? And this picture is represented as a metric. So this metric is a mathematical representation or modeling of the data. But if you say, I want to more interested about the detailed facial expression instead of the hairstyle, so many people can choose this kind of characteristic point. And when you choose this characteristic point, you translate this data into this point in the cloud representation. Definitely, you can do this mesh representation. This is called a heat map and eigenface. So essentially, the same data can end up in different mathematical representation, and this will, result in different learning architectures. And the second part is this feature learning. So essentially, how you obtain the most relevant feature to the problems. So if you study a little bit of biology, you may heard about the word biomarker, right? So if I want to check this guy got cancer or not, I have many different things I can measure. Right? I can measure his body weight, I can measure the height, I can measure the blood type, all these things. But only several features are directly related to if this guy got cancer or not. This is what they call a biomarker. And biomarker is exactly this kind of features you want to learn, okay, in the AI business. So when you go into the molecular science, it's the same game. First, how to represent molecular, right? So you get a molecular, actually there are various different ways you can check it. First is this sequential representation, just as we mentioned, right? You have this ATGC amino acid sequence. It can also, this nucleic acid sequence, it can also be the amino acid sequence. You can, if it's small molecular, you have this smell sequence. Or you see in this conference, we have a lot of people talk about the linking number, talk about the twisting information. Then in this case, I want to represent my molecular as a chain. Okay, so you can have this 2D, you have this chain embedded in 3D space, and then you can study maybe knot and all this kind of information. Or I think the most common one you see is this graph representations. So essentially, you can model each atom as a node, and then you have the edge represent the covalent bond. So if you Google any molecular, then this may be the picture you see the most. Right? This is a topological representation. Or you can go this kind of surface representation. So I have each atom I associate with a sphere, when the one sphere, and then the outside region of this sphere will give you a surface representation. And with this surface representation, definitely you can talk about the surface area, what are the angles, what are the curvatures, all these things. And the last one is this, function representation. So I think you guys will heard about quantum information, right? So then, electron distribution, these kind of things. You can use density function and then get this kind of function representations. And then when you have this different type of representation, you will end up in different learning models. And another thing is that you can take out different features from different representations. Okay, this is actually already been widely studied. People call it chemical descriptor, molecular descriptor, chemical fingerprint, molecular fingerprint. Actually, other than this physical type of features, a lot of them are related to structure. Actually, more than 5,000 of these structures has been proposed. They are like a 0D molecular descriptor, 1D descriptor, 2D, 3D, and 4D. Okay, and then even whole area called QSAR, quantitative structure activity relation, has been developed. Okay, so you may wondering why people interested so much about the structure. So this is because that, okay, something going here. Yeah. They block these things. Let's see. Close this door. Yes, now it's okay. So essentially is that when you have this, you want to interest to study the functions, but a lot of time people focus on this descriptor, structure descriptor, is because you have this something called a structure-function relationship. If you can understand the structure very well, usually you will say a lot about these functions. So for instance, I have these guys here. You may know nothing about this, protein, right? Just the only thing you may have is that, okay, somehow there's a big hole in the middle, right? This is a major structure properties, but why you have a big hole in the middle is actually because this guy is seated in cell membrane and it allows the ions go from extracellular to the intracellular. So these holes, facilitate this structure host facilitate the function properties. So there are many other examples. I will not go to the detail, but essentially, when you characterize the structure very well, you will be able to say much more about the functions. Then the question is that when we have such a great amount of structure properties, right, structure informations, what can be, or is it possible that we can find some structures that are most intrinsic, most fundamental, that may characterize the most general property of the molecule? So this led us into the study of topological data analysis. So TDA, the key idea is to use the topological invariant to characterize or to describe the structure. So there are three major characteristics here for the TDA. First one is that they use this simplicial complex representation. So in fact, outside the math, people usually talk about topology in terms of graph, right? So you will have like a certain pairwise interaction, then you connected two nodes with the edge. That's what you see widely in social network, in interaction network, traffic network, this kind of things. And we know that this kind of pairwise interaction can be generalized into higher order interactions represented by simplexes. So for instance, we can have these two simplex made of 3 points, and geometrically it can be realized as a solid triangle. Okay, and then you have tetrahedrons made of 4 points, geometrically can be realized as a solid tetrahedron. And you can see that when you have a triangle, you can talk about the surface area. When you have the tetrahedron, you can talk about volume. But in the graph, it's challenging for you to define area and volume, this kind of high order informations. So this is the one advantage. The other one is this topological invariant. Okay, so here the key thing is usually this Betty number. Betty 0 is the connected component. Betty 1 is number of cycles or tunnels in the structure. And then Betty 2 is a certain sphere. So you can view it like football, and then inside is empty. Then this will give you a Betty 2 number. And this kind of topological invariant is very useful because when you are using the machine learning models, usually you want to train it in a certain data set and then use it to predict some new data, right? So in this way, what you want is to learn the most fundamental information within this data so that it can transfer into another systems. So if the feature you learn is very superficial, right? It's very, covered only in the partial information, you translate to another system, then it won't work very well. This topological invariant, they characterize the intrinsic information, so usually they have better transferabilities. So this will significantly enhance the performance of the AI models. And the other thing is this kind of multi-scaled representation through this filtration process. So here what's going on is that I have 14 points. Each one is associated with sphere, and then the radius sphere is systematically increasing. This is a corresponding simplicial complex, and then this is a barcode. So the x-axis is the diameter of this sphere. So originally you see I have 14 balls, and I have 14 bars here. Each one represents a sphere. But now when the two spheres overlap, they will form an edge here, and then the individual component will decrease by 1. So you go here, you only have 13 bars. And when you have more and more overlapping with each other, then you have more and more edges. And then in this way, the individual component will keep on decreasing. So essentially, when 2 balls overlap, you will form an edge. When 3 balls overlap, you will form a triangle. 4 overlap, then you will have a tetrahedron. Okay, so this is the Viatori-Sweep's definition. And then when you have a certain cycle form, then you will contribute a bar in this Betty 1 diagrams. Here you have 2 cycles, then you have 2 bars. So essentially, this is the information you can gain from this process. The length of this bar is roughly the size of this cycle. And then at each diameter, you count the number of the bars. It will give you the corresponding Betty number and the different diagram. Okay, so that's all the information you get is through this process. And actually, biologically, what's really going on is that for this Betty 0, if we check about this carbon-free molecular, so this is what they call the football type of fullerenes. So it's this kind of shape made of 12 pentagon and 20 hexagon structures. So first, we check what is the Betty zero bars. So you see the Betty zero bars here, there's nothing special. This is just a carbon-carbon single bond. This is, carbon-carbon double bond. This is just carbon-carbon single bond. And then here, this is represents the pentagon, the short bar, and then this hexagon is represented by this long bar here. And then you have a very long bar here just to represent this sphere shape. So that's the information you can obtain. And then if you are checking the molecular structures, you will see that, for instance, in DNA, I have some short bars here. This will represent the pentagon and the hexagon structure in nucleic acid. And then the longer the bars come later. This represents certain pairwise formed cycle in the minor or major growth structures. So with these things, actually, you can design the the simplicial complex for the data, and then you use the filtration, and then you can barcode. You can take the feature from the barcode, throw into the machine learning. So this is what they call the TDA-based machine learning models. These things has already been applied in various molecular data analysis, in particular drug design, and then they have very good performance compared with existing models. In particular, in this D3R Grand Challenge, Gowei has done a lot of nice works and then showed great advantages. And in particular, in the COVID-19 cases, when they studied the mutation of different virus, and then among thousands of these nuclear residues, they found two using these TDA models, and these two has been later found to be related to really all the mutated types. So this really demonstrates the advantage of these topological models in characterizing the structure and then do some predictions. So build on this success, we are trying to say, other than some of the topological models, if the other representations can also play some role. So here we check about the spectrum models. So go from spectrum graph, we go to spectrum simplicial complex and the spectrum hypergraph. So the idea is roughly like this. So if you have a simplicial complex, correspondingly, you can build up the boundary operator. So this is, the relation between the edge and the node, the relation between triangle and edges. And then from this boundary operator, you can actually construct something called a Hodge Laplacians. So what's going on here geometrically, compilatory is like this. So L0 for this zero-dimensional Hodge Laplacian, it tells you the load relation. So essentially, 1 connected with 2, then you put a negative 1. 1 connects 3, you put a negative 1. And then for this 1, you have 2 edges, so the node degree is 2, so you put it here. So that's the common, what they call a graph Laplacian. And actually, you can generalize this relation into the edge level. So here, this L1 basically gives you the edge connection, right? But the different from the node level, edge and edge connection is slightly complicated. So you have two situations. First is that like edge 1, 3, 1, 2, they are connected through a common node. So this is what we call the node adjacent. And then you can have 2, 3 and 2, 4. They are within the same triangle. So this is what we call the upper adjacent. And then using this upper and the lower adjacent relations, you can design this kind of special Hodge Laplacians. Okay? And if you go further to say, what are I calculate at eigenvalues, you will find that the multiplicity of the zero eigenvalues. So you just count how many zero eigenvalues in this Laplacian, they will correspond exactly to the Betti lambda. Okay, so the lambda multiplicity of the zero eigenvalue gives you the topological information. And definitely you can check about the non-zero eigenvalues. They will have much more fluctuation. They can characterize more detailed change in the structures. And what we do is combine these features with the learning models, and then we study this protein ligand binding case, which is a very important step in drug design. So usually you want this drug bind this protein strongly, but not to other proteins that are irrelevant with diseases. So in this way, you design a highly efficient drug, and we found it actually works quite well. And another thing we are checking is this kind of rich curvatures. So essentially, there are different ways to describe this rich curvature into the graph or simplicial complex setting. Right, so there are something called Oliver rich curvature or Foreman rich curvatures. I will not go to the detail, but very roughly speaking, these curvatures characterize the similar pattern like this. So essentially, if you form a certain cluster in the structure, usually you will have highly positive rich curvatures. And then if you are the link regions between the two clusters, then you will have a highly negative curvature. So usually in this community, people usually what do is that they find this highly negative rich curvature region, and then they cut off all these edges. Then they get several clusters. So you can use that to find out the community, do these things. And what we did is that we still build up a filtration process, and then we get a rich curvature, and then we study the change of the rich curvature along the filtration process. So we use this information, the change of curvatures as a feature, and then throw into the machine learning models, and we found it actually also worked quite well for many of the data we studied. And this is not surprising because these three models are highly connected. So for the Hodge-Laplacian, the spectral model, if you do the Hodge decomposition, you actually get the Betti number information, just as we said, right? Because the harmonic part related to the topological invariant. And then another thing is that the Hodge-Laplacian and the Foreman rich curvature can be connected through each other through this combinatorially Bochler-Laplacian relations. So in this way, these three features, geometrical feature, more like a spectrum feature, and the topological feature can all be used to characterize the systems. Actually, if you want to play a little bit more deep learning models, all these things can be used as a certain score functions. So they can help you to tune your deep learning models to obtain certain essential informations. So that's what we are saying here. So other than these features, you can also check about different polynomial, different topological or algebraic invariant. All these invariant can be used not only as features, but also as a way to define a special score functions. So for instance, I want to generate an image that is highly symmetric, right? So this symmetric information can be characterized by maybe certain group information or algebraic information. And then you can use this algebraic invariant as a constraint in your AI learning models. This will help you, get great efficiency when you are designing the models. So all these things about features, but as I mentioned, another key important is the representation. Right? When you get the data, how you translate it into the right mathematical models. So previously, as mentioned, people usually use this covalent bond-based graph representation to represent molecular structures. But if you do a little bit of machine learning models, you will see that this model is actually quite inefficient in study the functions. The reason is that they miss a lot of non-covalent interactions. So in this way, we are trying to say that this graph representation is just one way for you to characterize the topology. There are many other different topological representations we can consider. So here are some of the games we have played. The first one is this neighborhood complex. So the idea is like this. So if I have a graph representation for a certain structure, I can try to generate a simplicial complex, a special complex from it called a neighborhood complex. So the idea is roughly like this. So you see here, I have a node here, and then this guy, these three nodes are the neighbors of this point. Then I form a triangle, a solid triangle, two simplex among these 3 points. And then for this point here, I have this point here, you have these 3 points, then you can form a triangle among them. So essentially, you find the labels of the point, and then you form the simplex among that. If you use a limited graph neural network, that's exactly what they do, using the labels to do the messenger passing. And the interesting is that when you have the neighborhood complex working on this bipartite graph, you will end up something called a Docker complex. Okay, so you see bipartite graph basically means that I have a certain atom here, a set, another set, and then the connections is only happened among the set. Okay, so this can be widely used to model the interaction. For instance, I want to study the interaction of this ligand with this protein. Then I have all these edges between protein and ligand. And then if you use the label code complex, you will see that all the labels for the green part come from the blue guys. All the labels of the blue point come from the green guys. So you end up in two separate complex. So this is what they call Docker complex. And the interesting is that this Docker complex will have similar topological features. So you see the barcode here and here are the same. Other than that, we can also check about this home complex. It's also a tool that Lavas used in study these conjectures. So the idea is roughly like this. So I want to study a certain graph G. So what I can do is find out all these kind of motif or subgraph structures. And then I try to use this one to work on these structures. Okay, so you can understand this like a test module. This is the real structure in interest, and then you see how this test module worked on these structures. And they use the mathematical tool called multi-homomorphisms. So essentially, you map the node from this test one to the original one. So for instance, I map K1 to A. And then I can also map the X2 to a certain point. If I map X2 to C, then it's okay because AC is the edge, and then here is the edge. But if I map X2 to A, then I have trouble because X1, X2 form an edge. Here, you don't have a self-loop. So essentially, using this kind of multi-homomorphism mapping, you can construct a simplex called a polyhedron complex. And this polyhedron complex will reflect the detailed higher order interaction of this test motif or subgraph within the structure you are interested in. So this is the home complex we are considering. And also with Prof. Wu, we are tracking this hypergraph representation. So the idea is basically like this. As mentioned, when we have this interaction from protein and the ligand, we can have this bipartite graph representations. However, these things are only pairwise interactions. So I only have one atom from protein, one atom from ligand. So this is just like a pairwise interaction between the two atoms. Now I want to incorporate higher order interactions. So what I can do? What I can do is that I form a hyperedge. So for instance, I pick these 2 points from ligand, 1 point from protein, then I have a hyperedge among these 3 points. Okay, you can also say I form a hyperedge among these 4 points. So in this way, systematically, I can have a series of these hyperedges that tells you the interaction between the protein and the ligand that are higher than pairwise interactions. And then from that, we have the special embedded persistent homology specifically designed for hypergraph. And these things has been shown to work very well in this kind of interaction analysis. So this is the one thing. And then another model we defined recently is called a joint persistent homology. So again, it's a similar idea. We want to study this protein K or a certain structure K. What I can do is to choose a certain test simplicial complex L. Okay, so K is something you want to study. L is like a test type of simplicial complex. So you can usually change this to say L1, L2, L3, L4, whatever. Okay, and then I can form the join between these two simplex. The idea is very simple. So you take all the vertices from K, you take all the vertices from L, then you have the vertex set for this join. And then all the simplex in this join is just take a simplex from K and then take another simplex from L, put them together. So in this way, you have the join of the simplex of these structures. And then the interesting part is that you can now design a multi-staged filtration based on this join. Okay, so the idea is like this. So you see, I want to study this structure. Previously, I can do a filtration, but this filtration will give you certain constraint. You are only do a filtration following a certain direction. So imagine, here, Vincent, we have the very beautiful mountains, right? You can view the mountain from different angle. Then you can have a better picture of the mountain. So that's exactly what we are doing. You see, I can view the mountain maybe from this top region, so I go from here. Or I can go the mountain from this angle, or I can view the mountain from the bottom part, or I can from the other angle. So then I can, through this multi-stage filtration, I can connect these several different direction of filtration together into a uniform framework. So that's what we have, along L0, L1, and LP, and then you can couple them together into this multi-stage filtration on the joint structure. So in this way, you can have a much richer information of the structure K here. Okay, so that's the idea of this joint persistent holding. Another thing we did recently is this cohomology-based growth of hostile distance. So the idea is basically like this. You see, for some of the molecular structures, you can clearly find that they have a lot of these loop structures. And these loop structures are the major component building blocks of this structure. And now what we can do is that we can represent each of these cycle structure using these cohomology generators. So if you have this hot Laplacian matrix you see before, and then you get an eigenvector of the zero eigenvalue, actually they will be associated with these cycles. So in this way, you have a series of cohomology generators, each associated with a certain cycle region here. And then what we can do is calculate the distance between these cycles. Okay, note that each cycle is a certain eigenvector, so you can define certain distance between the two eigenvectors, and then that will, this distance between different eigenvectors will give you a certain dendrogram. Okay, so if you are not from dendrogram, it's actually not complicated. Essentially, what it tells you is that if these two cycle, the distance is very short, right? So very small, then you see these two will form this kind of connection first. And then this point represent, say this one represent this one is like slightly away from them, then they will combine together. Okay, so again, in the dendrogram, when the distance are close, they will form a cluster. When the distance are far away, they will be aggregate together at the later stage. And in this way, you will form this hierarchical dendrograph representation. And then what we can do is that you can map in this diagram into a certain vector. Okay, so here you have only one edge, then it's one, here you have two, here's three, so on and so forth. So in this way, I can map my molecular into a vector representation, right? So you see, still the same game, give you a structure, how to model it into a mathematical representation. And when you have these vectors, actually you can use certain generalized growth of hostile distance. This is called ultrametric distance. So essentially, you have this protein, you map it into this vector representation Z. You have another protein, you map it into this representation Z. Then you can calculate the distance between them. So this is what we call a cohomology-based growth of hostile representation, and we can use that to study different materials, because in this material they have a lot of cycles, and then we can use these things to characterize their structure properties. So this is about different representations. And then when you have the representation, the immediate question is that can we go further to say about the learning models? Okay. Previously, we are do all this kind of feature learning, right? So we are design topological feature. We use the Betty member. We have the algebraic feature. We have all this kind of hot Laplacian eigenvalues. We have the geometric feature from the rich culture, all these things. But now in the AI community, they are basically saying is that they want a learning architecture that is so powerful so that they can learn all these things by themselves instead of teach by human being, right? So the idea here is this kind of geometric deep learning model. So essentially, for this kind of models, they are trying to build up learning architectures for graph structures. In particular, the structure is represented by a graph. Okay, so here you see they have a certain graph, And then the learning is basically done in this way. So essentially, I have A here. A will have 3 vertices, 3 labels, B, C, and D. So essentially, they will say, okay, I have B, C, and D. They will contribute information to A. So you can imagine in this way, your behavior is influenced by all your friends, right? All the people connected, your family, your friends, all the people you know. So then how your behavior will look like is directly related to all your friends, family, and the people you know that directly connect with you. So then you use all this information from your friends, your family, the people you are closely related to update the information. So that's the idea. And then you keep on repeating this process. Your friends will also have friends, and then their behavior also influence the performance of your friends, and then you can iteratively do this process. So this is what they call the message passing, neighborhood-based message passing. And you can design these geometrical models. And one particular problem is that when this network have this kind of bottleneck region, they will have something called overscorching. So the information to go from here to here, you have to compress. It's just like a narrow bridge, right? So you want to go through a bridge, then you have to somehow, move in a different pattern. And then this overscorching region, people usually use rich culture to characterize it. And then when you put this rich culture information into the learning architecture, then you will usually have a better performance. So other than that, we are trying to say that for different regions, sometimes they have different behavior, and how can we characterize this connectivity information more analytically. So essentially, you can imagine this way. For these people in this class, you may have a very large cluster when each people is connected with tens or thousands of people, or you have a small cluster, even they connected, but they only have like 5 or 6 different people they related. So how to tell the difference between these two situations? We are using this analytical torsion to study that. So essentially, how complicated of this local structure is regarded as what are the dimensions they require to embed this structure into. So if your structure is very simple, you have only like 3 points, you can easily embed it into a R2 space. But if you have very complicated, like thousands of labels, then you need a much larger space for you to embed. And this information, we use this analytical torsion to represent it and throw it into the learning architectures. So this is another thing we do. And then eventually, building on this kind of learning ideas, we try to go to the real topological setting, the higher order setting. So this is what they call the topological deep learning model. So this is a very interesting research area between mathematics and machine learning. And the key difference is that in topological deep learning, people started from simplicial complex. Okay, so here is a simple illustration. So previously, when you have a structure, people usually represent as a graph. So when you have a graph, then you have this message passing and the node level. That's what they call the geometric deep learning. So again, in the geometric deep learning, the thing is that I have a certain node, then I find the neighbors, and then I use the label information to do this message passing, to do the information updating. So this is traditional geometric deep learning. In the topological deep learning, people trying to understand more about the higher order interactions. So that's why they will have information updating at the edge level and the triangle level. Okay, and edge level, just as we mentioned, right, is the same game. So for this edge, how to find its labels, right? So you see in our Hodge-Lap partition already mentioned that for edge, you can have a low adjacent, you can have upper adjacent. This will give you a definition of the labels. And then you can use the labeling information of this edge to update the information on this edge. So this is what they call the boundary-related message updating process in TDM. So similarly, you have triangle, you find the labeling triangle, and then use the triangle information to update the features on this triangle. And then you can collect all this information together and then throw into the machine learning models. Then you will see that it actually can work better than the existing graph-based models. And other than that, we are also considering certain material structures. So a key difference between the molecular data with like protein DNA, traditional molecular data, is that they will have these periodical structures. Okay, so usually what they do is that when you have a very large, molecular structure, they usually decompose it into this unit cell. So you have this unit cell, and then you can repeat this unit cell many, many, many times following a certain periodical conditions, then you can get the real crystal structure. So in order to incorporate this periodical information into the topological representation, previously people used this Gaussian graph idea. Okay, so how to do that? Essentially, in the Gaussian graph, the idea is that I find the atom of the same type or put a certain relations. So in this setting is that all these atoms of the same type are equivalent to each other. So then you can use a Gaussian process to merge of them into one single node. So when you are merging them into this single node, you do not change the edge relations. So you see here, I have 8 points. I merge them into the same node, but then the edge is still the same. So here you have a one edge between them, one edge between them, one edge. So here you see you have 4 self-loop, because these 4 self-loop are all related to the node here. And then you will have 8 edges between this purple node and this green node, and then these 8 edges will appear in these settings. So what we do here is trying to generalize, again, this graph representation into the higher order simplicial complex representation. And when you are in the simplicial complex representation, you can also consider different relations, right? Then you can try to quote the structures of within the related equivalent to each other through the relations into the things. So here again, simple example, we still use this 8 point of the same relation. Then I call them. Then I will get this what we call a quotient cellular complex. So different from the quote graph is that we will have this extracellular simplex structures in the systems. Okay, so that's the idea. Through these quotients, you can try to incorporate the periodical information. Here is a more practical example what people really do in the calculation. So what they do is that you have the unit cell, and then they can repeat it many, many, many times into this supercell. And then in this supercell, they can, again, relate the atom of the same type into this unique point. In this way, this complicated structure is end up only 2 points. And then the edges between them are now characterized both intercellular interaction and intracellular interaction. Okay, so that's the key thing, because previously, if you just use the unit cell, then you can only see the interaction within this unit cell. That's what I call intracellular. But with this representation, you begin to see the interaction between the adjacent cell. That's what they call the intercellular interactions. And these intercellular interactions can be well characterized by some of the edges here. Okay. Again, in our case, we can do the same thing. We can generate a simplicial complex and then do the thing. But the slightly tricky part is that how can you define the simplex of the same relations, right? How to show that some of the simplex are equivalent to each other. So you can quote them based on the vertices, or you can quote them based on the edges or triangles, so on and so forth. So this can open up a lot of interesting mathematics in these settings. But with this kind of quotient complex settings, we can design certain transformer architectures and then incorporate these transformer architectures in this learning process, and you will see that it actually works better than existing models. One other things we are considering is this path complex representations. So essentially, when people study molecular structures in the computational chemistry or computational physics, they have something called a molecular dynamic. Okay, but this molecular dynamic stimulation has never been incorporated into the deep learning architectures. So here, what we're trying to do is to propose a certain like a physical informed deep learning architectures for molecular structures. And the physical information we want to preserve is from the molecular dynamic setting. So how do you think will work? It's basically like this. So in the molecular dynamic, they are trying to say that all the motion of this molecule is controlled by some basic component. The first component is this bond interaction, right? So you have say a carbon, this is oxygen, then it's a carbon-oxygen bond between them. So they use this kind of bond term to represent this one. And then the other one is called a bond angle. So you have a carbon, oxygen, maybe another nitrogen here, then you form a certain bond angle among them, and then this bond angle will contribute to another effect in the motion of the dynamic. Similarly, you dihedral term, and then this one, the Weyl interaction and the electrostatic interaction. So that's the building block for people to build up to study the dynamic of the molecular structure. So here, what we do is that we say, okay, I can choose a certain path, one path in the structure, and this one path is mimicking this bond interaction, and then some of the Weyl interaction and the electrostatic interaction. And then I can also choose the two paths here, use these two paths to mimicking this bond angle information. I can also go further to choose these three paths to mimicking this dihedral angle interactions in the systems. Okay, so again, when I have the structure, I do not randomly choose any three paths. I only choose the three paths that can reflect this boundary angle terms in the systems. So in this way, I will be able to say much more about the physical side of the system, and then my neural network is built based on this kind of physical setting of the systems. And with that, we can see that it actually can work better than the existing models. So the very last topic I want to mention about is our recent work on this multi-cover and the rhomboidal tiling settings for the topological deep learning. So this one is basically like this. So you have a bunch of points here, right? And then each point you can associate with a sphere, just like we do in this filtration business, no big deal. But then what you can see is that I can decompose these things into different, what they call the multi-covering representations. So here are the regions that has at least one boss, right? So this part, you have this ball, and then this part, you have ball. And then here, this is what we call one order cover. Here are the regions that are formed by at least two balls, right? Because you see this region is this overlapping between this ball and this ball, so on and so forth. So this, what we call the two cover, is the region formed by at least two balls. Similarly, you can have like a three cover, four cover, so on and so forth. And when you have this cover, further, what you can do is that you can design this K-order Borrowing diagram, and then you can get the K-order Borrowing complex. So essentially, you can decompose this, you can get the simplex from this structure. So this special one-order Borrowing complex corresponding to this one cover. This two-order Borrowing complex corresponding to the two cover. This three-order Borrowing complex corresponding to this three cover. Okay, so this, if you want to understand more, this is roughly about how can these higher order informations interact with each other, and topologically it's represented in this way. And more interestingly is that these three different, this series of the learning complex, they are tightly related to each other through this rhomboid tiling. Okay, so essentially, if you put this simplex here, put this simplex here, this one here, so on and so forth, what you will see is that the simplex in this K1 and the simplex in the K2, they can be somehow connected through this rhomboid tiling formula. And then all these simplex K-orders, the learning complex, they will form a tiling of this special space formed by the, this dimension plus another k-order dimension. Okay, so and the key thing for this rhomboid tiling is that this structure is all built up from this rhomboid structure. So it's like a cubic, but slightly tilting. Yeah. So with this cubic slightly tilting, is that you will fill the entire space by this building block. And following this building block, actually, you can trace the relations between different simplex and different orders. And then you can, in our case, we can design a certain pooling or message passing mechanisms. Okay, so this may look a little bit abstract, but very roughly speaking, for this k equal 1, k equal 2, what are the difference in the Betti number they see? Okay, so for k equal 1, you can imagine the Betti 1 cycle is just formed by the overlapping of the cycles. So you can have cycles that is formed in this way. So I have balls here, 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 and here. Then I will form a cycle. This is the k equal 1 situation. In the k equal 2 situation is that you should have at least a 2 ball, then you can have the starting point. And then you should have another 2 balls here and then maybe here, and then you have another point, and then they fill this edge. So essentially, this point now in the K1 order is this 2 point in the K2 settings. And then in the K3 setting, this point here is made of 3 points. So you can imagine this way. If I use, this is my plate, and then this is one nail, right? I use one nail to connect this plate together. I form a cycle. This is k equal 1. But in k equal to 2, one nail cannot fix it. So you need 2 nails. Each of the nail represent one cycle. So this 2 nail means that this 2 cycle has to be overlapped. And then you have another 2 nail here represent 2 cycle. And this overlapping of the 2 cycle and the overlapping of the 2 cycle should overlapping again. So this will characterize more detailed higher order interaction formed topology in the systems. And building on this, you can have the all the related informations, and essentially you will see that you can have a better performance. So to quickly summarize, what we are trying to do here is trying to introduce tools from topology, geometry, algebra, and combinatory to for feature engineering, for scaling function design, and also for deep learning architecture designs. And this is my group. I will basically stop here. Thank you.
Thank you for the wonderful talk. Are there any questions in the audience? Yes, please.
Question. So in quotient complex, how can I find the items that should be quotient? It's
yes.
based on data.
Yes. So that's a good question. So essentially, in the quotient complex, the reason we want to use quotient is to represent the periodical information. Yeah. So you can imagine I have a unit cell here. I may have another unit cell here, right? Through this kind of periodical boundary condition. So in this way, I would assume the point here is equivalent to a point in this another unit cell. So in this way, they are equal to each other. So essentially, you can understand this that the periodical condition gives you way a certain equivalent relations. So along this periodical orbital, they are in the same place, then you can quote them together. But definitely in our, if you consider this simplicial complex, you have a large degree of freedom to do different way of defining the equivalent relations. Yeah, but here this will be more mathematical game where they have like interesting material meanings or physical meanings, then we need further studies.
Any other questions in the audience? Yes, please.
Very naive question. You started from AI and you arrived to mathematical AI. So what about non-mathematical?
I think again, as mentioned, I believe that now AI has gradually go from this kind of general architecture design into more deeply understanding of the physical world. So, for instance, people are now study the moving of the robot, how this the robot dog was running, right? So then they need to understand the physics. It's not just like understand the image, but then the physics behind the image. And then a lot of time, the physics is represented by the corresponding mathematical equation. For instance, when they want to study the running, they have the very famous video when the three dog was running, and then suddenly a fourth dog coming from nowhere. So this kind of things does not, conserve the basic physical property because there are three individual components. But now, if you can introduce a certain invariant or certain way to preserve these physical properties into the systems, then it will help the AI models to learn better about the world. And we believe this kind of physical information should all be incorporated or understand from these different mathematical representations. Yeah.
Say social network would be something given the law, presenting now we want to put some laws on the data.
Yes, yes. We want to at least make sure that the generated result will follow in certain laws. Because now the trouble is, they say the garbage in, garbage out, right? So you have data, you can always generate something. But will this generated result satisfy certain general physical or mathematical constraint? And these constraints somehow can be incorporated into the learning models when the more mathematical settings get into the settings. Yeah.
Are there any more questions from the audience? Okay, let's thank the speaker once again for a wonderful talk.
Okay.